Hi, today I prepared another population genetics video, and here is a problem. We start with hypothetical population where frequency of the capital A allele is 0.6 and frequency of the small a allele is 0.4, and assume that homozygous dominant and heterozygous genotypes has relative fitness 1 and homozygous recessive genotype has relative fitness of 0.1. In other words, 90% of the homozygous recessive offspring die without reproducing. What is the frequencies of the dominant allele A and recessive allele would be in F1 generation? And if you feel that you know how to solve this problem, you may stop video here, try to solve this problem on your own, and when you would be ready, you can run video again, and you can compare your answer with my answer and explanation. And first of all, in order to solve this problem, I'm going to use Hardy-Weinberg formula, and that give us frequencies of the different genotypes that we can get from two alleles. So what is this genotypes? And here is a formula: p squared plus 2pq plus q squared, and all this equal to 1. And for the p squared we have homozygous dominant genotype. For the 2pq we have heterozygous genotype, and for the q squared we have homozygous recessive genotype. Also, you have to know that all the alleles p plus all the alleles q that we can find here in this formula in the form of homozygous dominant and 1/2 in the heterozygous form. This is all the alleles that is capital A, and here in this formula for the capital A stands P, and for the Q we have allele that is small a, and we can find this allele in the homozygous recessive form, and 1/2 of the alleles in the heterozygous form also would be small a allele. So all p alleles plus all q alleles would also equal to 1. So now we can use this formula to solve our problem. And we know that capital or dominant allele A, its frequency is 0.6, so we can put this frequency here. So this is going to be 0.6, and frequency of the small a allele is 0.4. So this is frequency of the small a allele, and as you see, if we add these numbers we are going to get 1. So far so good. And how we can use this information to find frequencies and how we can apply for this formula. So as you see, q allele equal to its frequency equal to 0.4, and here in the formula we have q squared. So now we can find homozygous recessive knowing this number. What we have to do, we just have to multiply 0.4 by itself, or square it. So we are going to get 0.16. And this would be frequency of the homozygous recessive genotype, so 0.16. Now we can also find p squared, or homozygous dominant. So this is homozygous recessive, and this is homozygous dominant. What we have to do, we just have to multiply this number, that is 0.6 by itself, 0.6 by itself, or square it. So we are going to get here 0.36. So this is going to be frequency of the homozygous dominant. So this is 0.36. And now we also can find frequency of the heterozygous genotype. What we have to do, so frequency of the 2pq or heterozygous genotype would be 2 multiplied by number p, that is here 0.6, so we have to multiply by 0.6 and multiply by number q, that is here 0.4, and the number here would be 0.48. So the frequency of the heterozygous genotype is 0.48. And now if we add all these frequencies, as you see, we are going to get 1. So far we find all the frequencies of all the genotypes, and now we can move on and let me clean a space here a little bit. So we know that according to our problem that the fitness of the homozygous recessive genotype is 0.1. In other words, 90% of the homozygous recessive offspring would die without reproducing. So what should we do? We just have to use this information in order to find F1 generation frequency. So we are going to use the same formula, Hardy-Weinberg, but this time we have to multiply all the frequencies by the relative fitness. So here is the formula, once again, p squared multiplied by W capital A, and W stands here for the relative fitness, plus 2pq multiplied by W capital A, small a, by relative fitness of the heterozygous genotype, plus q squared multiplied by W small a, and as you see, relative fitness of the homozygous dominant genotype is 1. Relative fitness of the heterozygous genotype also 1, and relative fitness of the homozygous recessive genotype is 0.1. So now we can use once again all the information and frequencies that we got here in our first step. So let me rewrite this formula. So frequency would equal to 0.36 multiplied by 1. So this number is not changing. Anything multiplied by 1 is the same number. And here frequency of the heterozygous is 0.48. So 0.48 multiplied once again by the relative fitness 1, and this would be the same number. And here for the homozygous recessive genotype we have to multiply 0.16 by 0.1. So what we are going to get here, we are going to get here 0.016, and these numbers stay the same. And this is our genotypes. So if we add all these numbers, unlike in our previous example where we got 1. This time this is going to be different number, and the number here is 0.856. So but as you see, according to the formula, we have to get here 1, and we got here 0.856. So we have to make all our calculation in such order that we should get here 1. How we are going to do it? We are going to once again divide the frequencies here that we have for the homozygous dominant, for the heterozygous genotype, and for the homozygous recessive by this number. Let's try to do it and see what we are going to get. So here we would have frequency once again would equal to for the homozygous dominant genotype we have to divide 0.36 by 0.856, and new frequency going to be 0.42. For the frequency for the heterozygous genotype would equal to 0.48 divided by 0.856, and the answer here would be 0.56. And for the homozygous recessive genotype, that is small a, we are going to get 0.016 divided by 0.856, and the answer here would be 0.019. Now let's check if we add all these new frequencies. We are going to get 1. So 0.42 plus 0.56 would be 0.98 plus 0.019. This is almost 1, not 1 exactly, but very close, so we can round this number to 1. So far so good. And now we have left only last step. We have to find new frequencies of the A, capital A and small a alleles. So once again I want to remind you that P plus Q equal to 1, where P is all the alleles capital A and Q all the alleles that is small a. And the frequency of the homozygous dominant genotype, new frequency would be 0.42. So let me write this down, 0.42. This is frequency of the dominant allele A in the homozygous dominant form, but we also have some dominant alleles that is capital A in the heterozygous form, and here is a new frequency, so we have to add 1/2, because half of the alleles here would be dominant A and half would be small a allele, so we have to divide this number by 2. So this is going to be 1 half multiplied by 0.56. And the answer here would be 0.42 plus 0.28 or 0.7. And according to our formula, if we know P, we can find Q. Just we have to deduct 1 minus P, and this is going to be Q. So this is P, and Q would be 1 minus 0.7 or 0.3. And this is going to be frequency of the dominant allele A, and this is going to be frequency in new F1 generation of the recessive allele, that is small a. So this is our answer. For the dominant allele capital A, and here is our answer for the recessive allele A, small a. And this would be new frequencies, and if we return to our problem, you would see that the frequencies that we start with were 0.6, and for the recessive allele 0.4. So as you see, selection against homozygous recessive genotype, that is would be 0.1 relative fitness, would give us this new frequencies in F1 generation. Thank you for your attention. Please subscribe for my new videos that I post almost every day. Thumbs up if you like this video. Goodbye.